Hello students, welcome to the lecture on relation and function, and after the lecture we will be able to learn the following objectives. Define types of relation, discuss the types of function, discuss composition function and invertible function, define binary operation. Let us start with the introduction of the relation and function. Recall that the notion of relation and function, domain, codomain and range has been introduced along with different types of specific real-valued functions and their graphs. The concept of the term relation in mathematics has been drawn from the meaning of relation in English language, according to which two objects or quantities are related if there is a recognizable connection or link between the two objects or quantities.
With a definition of a relation. A relation is defined as any set of ordered pairs. Here I have 1, 2, 3, 4 ordered pairs. Now the reason that they're called ordered pairs is that the order within the pair is very, very important. The x coordinate is always the first one and the y coordinate is always the second one. A lot of work in this lesson will be done with domain and range. So let's find out what that's all about. The domain is the set of the first members of the ordered pairs. In other words, all possibilities for x. The range is the set of the second members of the ordered pairs. In other words, all possibilities for y. Example 1. Find the domain and range of each of the following relations. Now, in this example, you're actually given a complete list of the ordered pairs in the relation. So it's pretty easy to find the domain and range. I know that the domain will be all of the first members of each of the ordered pairs. In other words, all the x's. So I will write 2, -1, 4, 3. And that's it. There are 4 members in my domain. The range now will be the set of all the second members of each of the ordered pairs. That means all the y's in the relation. So 1, 3, 2, and -2 make up the range. In the B part, you have another relation with 1, 2, 3, 4 ordered pairs, and again you're asked to find the domain and the range. The domain, all of the x's, -3, -1, 0, and you come to this last one and you see another -3. You do not write that down. If it's down once, that's it. So there are only 3 members in this domain, -3, -1, and 0. The order in which you write these down makes absolutely no difference, as long as they're all there. The range now, the y's, 0, another 0, don't need that, 1, another 1, don't need that. So the range becomes 0, 1. Example 2. Find the domain and range. It becomes a little more difficult to find the domain and range if you're given the graph rather than a list of the ordered pairs. So you have to look at the graph and see what x values were used and what y values were used. I want you to notice that this graph has points only. Nothing in between the points. So I can see that I'm using 1 for x, but certainly not 1.5 or 1 3/4. 2 and nothing in between 2 and 3. This is an example of a discrete relation where it's made up of points only. So in order to find my domain here, I could write out all the points if I wanted to, but I'm just going to have a look at what I can see from the graph. I can see that x is being used with this point, this one, that one, that one, and that one. And that's all. So x is 1, 2, 3, 4, and 5. So there's my domain. 1, 2, 3, 4, 5.
Let A be the set of students of class 12th of a school and B be the set of students of class 11th of the same school. Then some of the example of relation from A to B are, here A, B belongs to A cross B and A is brother of B. A, B belongs to A cross B and A is sister of B. A, B belongs to A cross B and H, A is greater than H of B. A, B belongs to A cross B and total marks obtained by A in the final examination is less than the total marks obtained by B in the final examination. A, B belongs to a cross B and A lives in the same locality as B. However, abstracting from this, we define mathematically a relation R from A to B as an arbitrary subset of A cross B. If A, B belongs to R, we say that A is related to B under the relation R and we write as A, RB. In general, A, B belongs to R. We do not bother whether there is a recognizable connection or link between A and B. Functions are special kind of relation. Here we will study different types of relation and functions. Composition of functions, invertible functions and binary operation. Let's talk about the types of relations. We know that a relation in a A set A is a subset of A cross A. Thus, the empty set phi and A cross A are two extreme relations. For example, consider a relation R in the set A is equal to 1, 2, 3, 4 given by as shown on the screen. This is the empty set as no pair A, B satisfy the condition A minus B equal 10. Similarly, R inverse is equal to as shown on the screen. Here the whole set A cross A as all pairs A, B in A cross A satisfy mode A minus B greater than or equal to 0. These two extreme examples lead us to the following definition. Definition 1. A relation R in a set A is called empty relation if no element of A is related to any element of A, that is R is equal to phi subset of A cross A. Definition 2. A relation R in a set A is called universal relation if each element of A is related to every element of A, that is R is equal to A cross A. Both the empty relation and the universal relation are sometimes called trivial relations. Definition 3. A relation R in a set A is called reflexive if A belongs to R for every A belongs to A, symmetric if A1, A2 belongs to R implies that A2, A1 belongs to R for all A1, A2 belongs to A. Transitive, if A1, A2 belongs to R and A2, A3 belongs to R implies that A1, A3 belongs to R for all A1, A2, A3 belongs to A. Definition 4. A relation R in a set A is said to be an equivalent relation if R is reflexive, symmetric and transitive. Here we will try to discuss about the types of functions. A function is a correspondence between two sets called the domain and the range, such that to each element of the domain there is assigned exactly one element of the range. The notion of a function along with some special function like identity function, constant function, polynomial function, rational function, modulus function, etc. along with their graphs have been given. Consider the functions f1, f2, f3 and f4 given by the following diagrams. In the given figure, we observe that the images of distinct elements of x1 under the function f1 are distinct, but the image of two distinct elements 1 and 2 of x1 under of 2 is same, namely b. Further, there are some elements like e and f in x2 which are not images of any element of x1 under f1, which all elements of x3 are images of some elements of x1 under f3. The above observation lead to the following definition. Definition 1. A function f x tends to y is defined to be 1 minus 1 or injective if the images of distinct elements of x under f are distinct, that is, for every x1, x2 belongs to x, f of x1 is equal to f of x2 implies x1 is equal to x2. Otherwise, f is called many one. The function f1 and f4 in figure first and fourth are 1 minus 1, and the function f2 and f3 in figure second and third are many minus 1. Definition 2. A function f x tends to y is said to be onto or surjective if every element of y is the image of some element of x under f, that is, for every y belongs to y, there exists an element x in x such that f of x is equal to y. The function f3 and f4 in figure third and fourth are onto, and the function f1 in figure first is not onto, as elements e, f in x2 are not the image of any element in x1 under f1. Definition 3. A function f x tends to y is said to be 1 minus 1 and onto or bijective if f is both 1 minus 1 and onto. The function f4 in figure 4th is 1 minus 1 and onto. Here we will study composition of function and the inverse of a bijective function. Consider a set A of all students who appeared in class 10 of a board examination in 2006. Each student appearing in the board examination is assigned a roll number by the board, which is written by the students in the answer script at the time of examination. In order to have confidentiality, the board arranges to deface the roll numbers of students in the answer scripts and assigns a fake code number to each roll number. Let B subset n, where n be the set of all roll numbers and C subset n and n be the set of all code numbers. This gives rise to two functions f of A to B and function g of B to C, given by f of A is equal to the roll number assigned to the student A and function g of B is equal to the code number assigned to the roll number B. In this process, each student is assigned a roll number to the function f and each roll number is assigned a code number to the function g. Thus, by the combination of these two functions, each student is eventually attached a code number. This leads to the following definition. Definition 1. Let function f of A to B and function g of B to C be two functions. Then the composition of f and g denoted by g of is defined as the function g of A to C, given on the screen. Let's discuss about the binary operation. Right from the school days, you must have come across four fundamental operations, namely addition, subtraction, multiplication, and division. The main feature of these operations is that given any two numbers A and B, we associate another number A plus B or A minus B or AB or A by B. B is not equal to 0. It is to be noted that only two numbers can be added or multiplied at a time. When we need to add three numbers, we first add two numbers and the result is then added to the third number. This addition, multiplication, subtraction and division are examples of binary operation, as binary means two. If we want to have a dual definition which can cover all these four operations, and the set of numbers is to be replaced by an arbitrary set x, and then generally binary operation is nothing but association of any pair of elements A, B from x to another element of x. Definition 1. A binary operation asterisk on a set A is a function of asterisk A across A tends to A. We denote it as shown on screen. Example, show that addition, subtraction and multiplication are binary operation on R, but division is not a binary operation on R. Further, show that division is a binary operation on the set R asterisk of non-zero real numbers. Solution of this you can see on the screen. Definition 2. A binary operation asterisk on the set X is called commutative if A asterisk B is equal to B asterisk A for every A, B belongs to X. Definition 3. A binary operation asterisk A cross A tens A is said to be associative if A asterisk B asterisk C is equal to A asterisk B asterisk C for all A, B, C belongs to A. Definition 4. Given a binary operation asterisk A cross A and tends to A, an element E belongs to A. If it exists, is called identity for the operation asterisk if A asterisk E equal to E asterisk A for all A belongs to A. Now in the end, let us summarize what we have learned in this lecture. Recall that the notion of relation and functions, domain, codomain and range has been introduced along with different types of specific real valued functions and the graphs. If A, B belongs to R, we say that A is related to B under the relation R and we write as a RB. A relation in a set A is a subset of A cross A. Thus, the empty set phi and A cross A are two extreme relations. A relation R in a set A is said to be an equivalence relation if R is reflexive, symmetric and transitive. A relation R in a set A is called reflexive if A belongs to R for every A belongs to A. A function is a correspondence between two sets such that to each element of the domain there is assigned exactly one element of the range. The notion of a function along with some special function like identity function, constant function, polynomial function and so on